Hey everyone, welcome back to a new week. I wanted to make a separate kind of introductory video today because, to be honest, the topic that I'm introducing this week, or this right now actually, is one of the most important topics that you'll see in calculus. And I say that because if we think about first trimester, everything in first trimester was about derivatives, right? Your entire final exam in trimester A was all about finding derivatives, taking derivatives, finding the slope of a line that's tangent to a curve, okay? This topic that I'm about to introduce today deals with area under a curve. So there's really any calculus class that you take, whether it's in high school or whether it's in college, if it's Calc 1, which you guys are obviously in right now, there's really going to be two main topics that are covered. One is derivatives, which involve slope of a line tangent to a curve. And two is area under a curve. Okay? So our essential question today is how can the area under a curve be approximated graphically? And there's going to be a worksheet uploaded that you'll have to submit when you're complete. Also, just a reminder that we're also going to have our usual knowledge check this Friday, okay? So let's start talking about area, okay? Up to this point in math, there are any number of common shapes that we've learned how to take the area of. I just wrote a few of them down here. So right triangles are 1/2 base times height. Rectangle squares, length times width. Circles, obviously pi r squared, and there's any number of shapes, whether they're trapezoids, whether they're oblique triangles. They all have formulas on how to take the area of these, right? You've done these in geometry, you've done these in algebra. These are formulas that, if you haven't memorized them, you've probably seen them 100 times before, okay? So how does this lead us into today? Because, as I've said a lot of times in my other math classes, is real world is not nice and easy shapes, okay? Straight lines, easy triangles, squares, rectangles, that's not the real world. When you're plotting something or graphing something in the real world, it's a much greater likelihood that you'll have data or you'll have, whatever you're working on, it's going to be more of a curve, okay? It's not going to be a straight line or a rectangle or a square. It's going to be a curve. And so the question today is, and this is kind of the big question, this is one of the things that calculus takes care of, this is one of the whole reasons for a calculus course, is let's say you have some distance from A to B, and you want to find the area underneath this curve. Okay, we can't use any of our formulas because this is curved, right? We want to take the area under this, but we don't have a formula for it, okay? Why is this necessary? Why would we want to take the area under a curve? I'll use an example that I'm sure we've all seen a lot of in the news and in social media and whatever else. If you've been half awake for the last 2 months, you may have seen or would have seen a graph of coronavirus cases, okay? So for example, I just made a sketch here of dates and number of cases. Again, I'm sure we've seen this in the news or social media where it'll give you a date and it'll say 300 new cases on this date, 500 new cases on this date, 1,000 new cases on this date, so on and so forth, okay? Well, that's fine. It tells us the number of new cases on a specific date, but what they don't tell you in the media and what they don't kind of reveal to you is the area underneath this curve, okay? If you were to find the area of this shape, that would give you the cumulative number of cases, okay? And what that would do, it would take the 300 cases on this day, the 500 cases on this day, the 1,000 cases on this day, the 2,000 cases on this day, so on and so forth, and it would add them together to give you the total number of cases, okay? That would be the area under this curve, okay? So that's just one real world example I wanted to give you as to why area under curves are so important, whether it's in science or engineering or technology, whatever it might be. It's really important when you're taking data. Okay, so to start, this is what we're going to be doing today. If you have a curve, and I'm just looking at the top one here. Let's say you have a curve. We're going to take the area of this curve today by approximating the area using rectangles. Okay, so let's say this is my starting point at A. Let's say this is my ending point at B. And let's say I want to find the area under this curve. What I can do is I can draw little rectangles underneath here. And the reason this helps is I know how to take the area of a rectangle. Okay, if I know this distance along the bottom and I know this height, I can multiply those together to get the area of this rectangle. I can do the same thing here, area of this rectangle, and I can add them all together to get an approximate area under the curve. Okay? And you're probably sitting there thinking, well, what about these holes in your equation here, right? We're missing spots. Okay? That's why all we're doing today is approximating the area under the curve. There is going to be missing pieces in our answer, and that's okay. We're just taking an estimate. Okay? Notice here that each of these rectangles touches the curve at its right endpoint. Okay, so I'm going to write right here, right endpoint rectangles. Okay, and again, let me go back to that. Each of these rectangles, if you look at their right endpoint, that's where it's going to touch the curve, and that's where it's going to go over to meet the other side, okay? Right endpoint, right endpoint, right endpoint, right endpoint. Okay, if you'll notice here, like we just talked about, when you get an answer, when you get an approximate answer for area under this curve, this is going to be an underestimate. And why is it going to be an underestimate? It's because you're missing these pieces right here, okay? If you're missing those pieces, those are all holes in your equation, or holes in your answer that you're leaving out, so you're going to be underestimating the area of the curve, okay? Similarly, if I go to the bottom part here, this is the same curve. However, the difference in this curve is these are left endpoint rectangles. Okay? And the reason I say that is, again, if you look at these rectangles that I drew, it meets the curve at the left endpoint of each rectangle. Okay? Just take this middle rectangle, for example. Here's the left endpoint, and then it goes over, and then it meets the left endpoint of this rectangle, the left endpoint of this rectangle, and they all connect. Okay? So if I were to take the area of this rectangle, add it to the area of this rectangle, add it to the area of this rectangle, so on and so forth, it would give me an approximate area underneath the curve. However, again, as you've probably noticed, these areas right here are all overestimates. Okay? These are all overestimates because that's not under the curve, that's over the curve. So this would be considered an overestimate. Okay? In reality, the true answer for area under the curve is probably somewhere between this answer and this answer. Okay? All right. I just want to show you just really quickly on the next sheet here that just because you have right endpoint rectangles doesn't always mean it's going to be an underestimate. Okay? It depends on the concavity of the curve. Okay? For example, these curves are concave up. Okay? They're like a U shape or a bowl shape. If I have a curve that's concave down, my right endpoint rectangles, meaning all these rectangles meet the curve at the right endpoint of their rectangle, this is all excess area. So this would actually be an overestimate. Okay? Similarly, if we're concave down, meaning up or upside down U, left endpoint, meaning my rectangles meet at the left endpoint right here and right here and right here at the left endpoint, I'm going to be missing all these spots right here. That's going to be holes in my answer. So this would actually be an underestimate. Okay? So the overestimate, underestimate piece of it all depends on the concavity of the curve. And this next chart I'm going to give you is something you're going to want to get in your notes because it's going to show up on the quiz this Friday. I'm just going to leave this here so you can pause the video and get this down. Okay? It's basically telling you if your function's increasing, your left endpoint rectangles be an underestimate. If your function is increasing, your right endpoint rectangles will be an overestimate. Same thing with decreasing. If your function is decreasing, meaning it's going like this, so increasing would be like this, decreasing would be like this, left endpoint rectangles would be an overestimate, right endpoint rectangles would be an underestimate. Okay, so that's all for this video. It was really important that I at least have an introductory video on this before I do some example problems because this kind of lays out the whole point of what we're going to do over the next few weeks. Okay, area under a curve is super important. So tune into our next video to get some examples on how to do the work today.